Welcome to Year 8 Competence-Based Middle Years Program Level 3 Sciences. This is workshop number 2. This is the second workshop devoted to going back to basics. And during this session, we will analyze uniformly accelerated rectilinear motion, or UARM. So, when solving a problem of uniformly accelerated rectilinear motion, UARM, there's a basic rule to follow, which is always start drawing a scheme as accurate as possible, choosing an origin of coordinates and a positive sense, and then stick to that choice. It won't matter what you choose as the origin of coordinates, what you choose as a positive sense, provided you do everything in a coherent way with that choice you have made. And in order to illustrate that, we're going to solve the following problem. A child playing with a wooden bird on a balcony throws it upwards to help it fly. Flight does not, of course, and the poor toy crashes on the street. The child had thrown it at 4.9 meters per second from a height of 9.8 meters above the street. Solve A. What height the bird reaches. B. How long lasts the last flight. And C. At what speed does it end its days? So again, the child is on a balcony, throws the wooden bird upwards, and then the wooden bird crashes on the street. Is that clear? Good. Let's simplify a little bit the text to focus on the important points. A child throws a body upwards at 4.9 meters per second from 9 meters high above the street. What is the height the bird reaches? How long lasts its flight from the moment it was launched until it crashes, and at which speed it crashes? So let's choose as the origin the street, the origin of coordinates. That's going to be height 0. And then we will use as positive sense upwards. Could be the other way, but given that the body starts moving upwards, we can use that as the positive sense. Now, again, remember the child is on a balcony at 9 meters above the street, and the street is level 0. So that position is 9.8. We represent that as the scheme in the image. We have a height that we do not know, which is the maximum. We have the initial height, which is 9.8. We have the positive sense, and we have the street, which is height 0, the origin of coordinates for this movement. So we have moved the scheme a little bit to our left-hand side so that we have space to solve the problem. And on the scheme, we can see the child, which is at 9.8 meters, positive 9.8 meters, because the origin of coordinates is the street and the positive sense is upwards. Therefore, 0 plus 9.8. And it throws the body upwards, and it reaches a height we call h, and then crashes down onto the street at height 0. This scheme contains all the basic information we know from the problem: the initial height, an unknown further height, and the final position, which is the street 0, and the positive sense that we have chosen. As we may well imagine, the maximum height is the point where the bird stops, because if it didn't stop, it would keep going up. Therefore, at that point, the speed equals 0. We know that once the child leaves the bird, launches the bird or throws the bird, the only effect upon that bird is gravity. Therefore, since it's been thrown upwards, it is a rectilinear motion, and it is with constant acceleration equal to gravity. It is a uniformly accelerated rectilinear motion. We have separated a little bit the two trajectories on the scheme so that we don't mix them up, but it would be a straight line. We know that the expression that gives us speed in terms of time in the uniformly accelerated rectilinear motion is v equals v0 plus the acceleration multiplied times time. Now, in this case, the acceleration is gravity, and gravity goes downwards. But we have chosen positive upwards. Therefore, it is a negative acceleration. We're going to put that sign, that minus sign, outside the g, so that g is just the value 9.8. So we rewrite our expression as follows. V equals V0 minus, goes down, the gravity times the time. And now we replace. We know that at the maximum point, the maximum height, speed is 0. We know that the initial speed is 4.9. It's 4.9 upwards, therefore it's positive. We know the acceleration goes downwards, and it is 9.8, therefore minus 9.8. And we're trying to find out the time it takes to reach that point. That is easy. In order to make the calculation, we add plus 9.8 on both sides of the equation, so that we end up with 9.8 times time equals the 4.9, the minus 9.8 times time, plus the 9.8 times time we just added, which is 4.9. Therefore, t equals 0.5 seconds. That's the time it takes the bird to reach the maximum height. And we will now use that value to calculate the value of height. Now that we know the time it takes for the bird to reach the maximum point, we can calculate the value of that point. We know that in the uniformly accelerated rectilinear motion, the position, depending on time, is given by the expression position r equals initial position plus initial speed times time plus half the acceleration times the time squared. If we replace the values, we have position equals 9.8. We're starting at 9.8 above the street, which is level 0, and upwards is positive sense, plus 4.9, which is the value of the initial speed, again positive because going upwards, times the 0.5 seconds it goes up, minus, because gravity goes down, a half of 9.8 times 0.5 squared. That is 11.025 meters, which we round up to 11 meters high. So the bird goes up a little bit more than 2 meters above its origin, and it stops, and then it starts falling down. We're now going to calculate the second part of the problem, the second question. How long lasts the flight? How long lasts the flight? Obviously, from the moment the bird was thrown to the moment it crashes. And that is simpler than it may seem. If we take into account that we know where we started, we know the speed at which we started, and we know where we end, and we know the acceleration. So let's insert all those data in the equation of the position and see what we come up with, and especially see what that equation means. So we say our final position, once the flight is completed is 0 because we come to the street level, which is the origin of coordinates. The initial position is 9.8. The bird was thrown from the balcony 9.8 meters above the street, and we have considered positive ascents upwards. It was thrown at 4.9 meters per second upwards, positive again, and there's some time that passes by. And the moment it is thrown, gravity starts acting upon it, and gravity goes downwards, so it is negative, and 9.8 meters per second squared, so minus a half of 9.8 times time squared. This expression, the way we have it, is a question we are asking Dr. Mathematics. And if we understand the question we are asking Dr. Mathematics, it will be very easy for us not just to solve the problem, which is pretty immediate, but also to understand how mathematics is the expression of physics in numbers, or the expression of science in numbers. So, our unknown here is time. Time is the answer we are asking Dr. Mathematics for. And the question we are posing Dr. Mathematics is as follows. What is the value of time, the unknown? What is the value of time that it takes the bird to be at point 0, final position, which is the street, origin of coordinates, if we start counting when the bird is 9.8 meters high, that's the initial position, and at that instant it is moving at 4.9 meters per second upwards, which is the initial speed, with a 9.8 meters per second squared acceleration downwards with a constant value. Again, what is the value of time at which moment for us to get to point 0, the street, the origin of coordinates, if we start counting the time when we are at 9.8 meters above the street, which is point 0, and at that instant we are moving at 4.9 meters per second upwards, positive, speed 0, whilst through the entire movement we have an acceleration downwards 9.8 meters per second squared, therefore minus 9.8. That is the question that we are asking Dr. Mathematics to obtain the value of time. Fine, that's the question we've asked Dr. Mathematics. And Dr. Mathematics comes back and says, look, what you are asking me corresponds to a quadratic equation. A quadratic equation which has the shape of a, coefficient a times the unknown squared, plus coefficient b times the unknown, plus an independent term c, and all that equaling 0. That is a quadratic equation. And when we have a quadratic equation, the values for the unknown, x in this case, which is the normal one in mathematics, is given by this expression. X equals minus b, the value of the coefficient of the unknown with the opposite sign, plus minus the square root of b squared, the coefficient of the unknown with power 1, minus 4 times the coefficient of the unknown squared times the independent term c, which is called the independent term because it's not multiplying the unknown. And all that divided by 2 times the coefficient of the unknown squared. So let's apply that expression to our case. Our quadratic equation was 0 equals 9.8, independent term, plus 4.9 times t, coefficient of the unknown to power 1, minus 4.9 t squared. Minus 4.9 is the coefficient of the unknown squared, so minus 4.9 is a. B is 4.9, C is 9.8. When we insert those values, we obtain t equals t now, because our unknown is called t, it's the time, minus 4.9 minus plus square root of 4.9 squared minus 4 times minus 4.9 in brackets because it's negative times 9.8 divided by 2 times minus 4.9 in brackets because it is negative. When we solve that expression, we obtain two values. One, of course, comes from using the positive value of the square root on the numerator, and the other one comes from using the negative value of the square root on the numerator, and that gives us two different values for time, which are as follows. Time equals minus 1 second, time equals plus 2 seconds. But hang on a minute, can time be negative? Or perhaps Dr. Mathematics has gone crazy? Or has not? And instead we need to make sense of those answers. So let's go back for a second to the question we posed Dr. Mathematics. We said that the moving body was at 9.8 meters above the origin, moving at 4.9 meters per second in the positive sense, with a constant acceleration of minus 9.8 meters per second squared. Constant acceleration. Dr. Mathematics is pretty rigorous, and when told constant acceleration is considered. But constant acceleration means not from that point. Constant acceleration could have been for Dr. Mathematics since the origin of the universe, and for Dr. Mathematics could be till the universe will end. If we consider that perhaps the bird was coming up from further down than the balcony, and we started counting the time when it passed by the balcony, and at that moment t equals 0 and position is 9.8, speed is 4.9 meters per second upwards, and the acceleration keeps being minus 9.8 meters per second squared, meaning it had been launched from further down, and it was going up more and more slowly until it stops, and then once it's stopped, it starts going down with a constant acceleration of minus 9.8 meters per second squared. And for Dr. Mathematics, it does not need to crash on the street because there might be a hole and the bird could go down very deep, if it will. And the answer Dr. Mathematics has said, on its theoretical way up, it would have gone by the level of the street at 1 second before you started counting at the balcony, would keep going up and then going down, reach the street again at plus 2 seconds, and keep going down. It could have been following that movement before t equals 0. But the answer we want, of course, is t equals 2 seconds. That's the time elapsed since the child throws the bird upwards and the bird crashes on the street. Let's now consider the final question, the speed at which the bird crashes on the street. That's a pretty straightforward one because we just calculated the time this bird had been moving since it was launched until it crashed, and that was 2 seconds. We know that the expression for speed at the uniform acceleration rectilinear motion is v equals initial speed v0 plus acceleration times time. So the speed we want will be the initial speed 4.9 minus 9.8, the acceleration times 2, which is 14.7 meters per second. 14.7 meters per second, negative value because it is going downwards, and we had said that positive was upwards. Let us consider again question A and consider question C from a different point of view as an alternative way to solve these two questions. We know that with uniformly accelerated rectilinear motion, there is a relationship between the speed and the position, and that relationship is given by the following expression. The square of the speed at any point equals the square of the initial speed plus 2 times the acceleration and the variation of the position. Therefore, for the height at which the bird stops, the height the bird reaches, we know that the speed equals 0. So we can replace that 0 in this expression. We know the initial speed, we know the acceleration, and we can find out the value of the position, which will be given by the expression you have on the slide. For the speed at which the bird crashes on the street, we do not know that speed, but we do know where it crashes. It crashes at height 0. Therefore, for position 0, we can write that the square of the final speed equals the square of the initial speed plus twice the variation in the position, which is minus 9.8, because it ends at 0 and it starts at 9.8. So the answers are simple. In sciences, as always, enjoy. Thank you very much.